Namaste. Myself Sachchida Nand, Assistant Professor, Department of Mechanical Engineering, Uttara Institute of Technology. Today we are going to discuss in the progress mode of the atomic structure. Now we will discuss the crystal structures at one step ahead to the component structure. So in last class we discussed about the various atomic structures and how they are working in their system, and because of that working, the properties of particular material is behaving. So according to that, we can say any structure of any material is related to the property of the material, and that is the reason we are discussing all these things in that depth manner to analyze or to identify that how these things are working, how a material is behaving when we apply some kind of load on that particular material. It tends to enlarge themselves according to the load. It is started flowing the electricity from them. It is started to maintain the high temperature. How all these things are possible? It is just possible because of that particular atomic arrangement. The atoms which are having their internal energies, and due to that energy they are jumping from one place to another orbit and attract the various atoms of other materials to construct a structure which leads to its properties, and that properties will withstand with that particular material, or you can say the component which are made by that particular material is sustained during their working environment, or you can say in the working environment of that particular component, and that condition of that particular component is all beared by that particular material, and it is just happening due to that atomic structure, and because of that atomic structure the property of that particular material is working. So in that continuation we will move to the one step ahead from the atomic structure to the crystal structure in the progress mode, that how it started to shape a solid material, to form a solid material or a material with the distinct properties. So in the previous classes we discussed about the atomic arrangement, so how these atomic arrangements are defining. So they are categorized, if we taking the example of only solid, a crystalline and the amorphous. So these are the two basic atomic arrangements. As you can see from the figure, the crystalline is a well-mannered structure and amorphous is not well-mannered structures, and that is how this leads to that particular kind of properties. In crystalline you can see this, the arrangement is in the perfect manner, but in the amorphous the arrangement is not linear. Some points are connected, some are not connected, and that leads to the another kind of a property to that particular material, and this particular arrangement leads to the another kind of particular property of the particular solid material. So if we are discussing about only the solid material, so that arrangement is defined in between two categories, that is the crystalline material and the amorphous solids. Sorry. So what is crystalline? As from the figure you can see the periodic arrangement of atom at a definite repetitive pattern. That the sequencing of that repetition, as that repetition is showing here, as that repetition, if you want to examine that things, you can see हिंदी में अगर कहें तो मधुमक्खी के छत्ते को अगर आप देखेंगे, so a kind of that arrangement, and you can see that arrangement is the very dense and very strong arrangements. So from that particular natural arrangement, you can examine how strong that particular arrangements are, and that the thing is crystalline material is also adopting that particular pattern to combine all the other all atoms in a systematic manner in the periodic arrangement of that particular. That is how that particular solid is playing a very crucial role and providing a various kind of properties. That is how that particular solid is to be defined by that particular word, the solid. So that is the arrangement of that in the periodical manner, that is defined the crystalline structure. And the non-crystalline or the amorphous structure, that the random arrangement of the atom, that is not in the sequence manner that you just fit that particular thing and that particular thing. But that is how that the non-periodic arrangements are managed. So the periodicity of the atom in crystalline solid can be described by a network of points in a space called the lattice. So now it's a very interesting thing. Now we are moving from that particular atomic arrangement to that crystalline arrangements. How that particular tiny particles are combining in the sequence to make a solid piece of that particular material. So what is space lattice? As you can see, these are the dotted point are showing the arrangement of the atom in the systematic manner, and that particular point A and B is providing the distance. They are the distance which is defining the things. We will discuss what is that particular A and B manners. So what is space lattice? It can be defined as three-dimensional area of a point, each of which has identical surrounding, obviously. And if the periodicity along a line A, then the position of any point along the line can be obtained by a simple translation RU, that is U and A. So similarly, RUV, that is UAVB, will be represent the point along a 2D plane where U and B is the integer. So internal, that is the integer of that particular thing. So how we are calculating the arrangements, how we are arranging that particular atoms, so that is happening by that particular space lattice. Now that space lattice lead to that, you can say that is the arrangements. So they are in the parallel manner, they are in the perpendicular manner. They are, as you can see from that particular figure, the unit cell is the combination and the arrangement of that particular atom, and that is, it is just only happen because of that space lattice. That is, they particular arrange themselves in a certain spaces at a certain levels of that particular coordinates. Because of that, the thing is to be managed, and that is how that atomic structure lead to the solid crystalline materials and provide a solid kind of properties. So the space lattice point in a crystal are occupied by atoms. The position of any atom in the 3D lattice can be described by a vectors, that the representation manner in the, you can say, mathematical representation manner. So that is a coordinate explain method, that is by these things. So the vector, that is UVW, that is are the coordinates which we are, that the integer is showing that particular things. So defined by that particular crystal system. So that is UA plus VB plus WC. These all are related to that particular coordinates, that is X, Y and Z, and that is how these particular things are to be examined. So the three unit vectors, as you can see, A, B, C, can be defined as shown by the figure in the shaded areas. That particular shaded area, that area is defining that particular things. This cell is known as the unit cell, and that is the particular things is showing that particular, that the thing is showing the unit cell, and that box is came from that particular point. that is in the space lattice. These are the solid arrangement of that particular, showing the unit cell of that kind of things, which will repeated in three-dimensional generate the crystal structure. And that is how these structures, as you can see, this is also lying here, this is also lying here, and that arrangement is in the systematic manner provide a solid crystal structure in the 3D manner. So what is Brava lattice? Brava lattice, the unit vectors A, B, C are called the lattice parameters that based on their length equality or inequality and their orientation, the angle between them, alpha, beta and gamma. A total of 7 crystal systems can be defined with the centering, the face, base and body center. Added to these, 14 kind of 3D lattice known as the Brava lattice can be generated. So these are the crystal structures, that is, you can see that is came from the unit cell, and that unit cell structure is defined by that particular crystal system as we discussed by that particular Brava lattice. So first one is the simple cubic structure. That cubic structure, A is equal to B is equal to C, that is means the alpha, beta, gamma coordinate is equal to 90 degree. So that is defined by the simple, that is the cubic centric, not the, I am just not talking about this simple, but these are the cubic system. That is how they are equally in manner because they are in the cube system, and that is how the arrangement of that particular atom is taking place. So that body centered cube is another form and the face centered cube is another form. We will discuss how these things are generated and how these things are linked that thing. So in these particular things you can see, you can examine these particular balls. These balls are the atoms. These atoms are arranged in this particular space lattice to maintain the balance, and that is how they are arranged in that particular things like this. So in that particular you see in the particular figures, as that is how these particular things are happening, and in the last figure, and that is how these structures are building. So these are the things which is showing, I just wanted to show that the thing is here, and that is how it works from here. So these are the 3 kind of cubic structures. That is how that A is equal to B is equal to C. Their parameters and their angles are equally distributed at 90 degree, and the arrangement of that particular body center means the all atoms are arranged at the corner and one in the center of the body, that is in the body center means. And that in the similar manner that the face center cubic, all arrangements are at the corner of the atom, corner of this particular system, and each one of at the faces, whether for one face, upper face, lower face, side face and bottom face, and that is how these all are arrangements are taking place, and that is the arrangement of that atom providing that particular properties of that particular material in that particular systematic manner. So in that things we are moving toward another kind of a cubic another kind of crystal structure, that is called the tetragonal structure. These are the arrangements, as you can see. This is the simple tetragonal and the body center tetragonal, that is the showing the angle of that particular thing. A is equal to B, but C is not equal. So that is how the arrangements are changed, and due to that change of arrangement, the structure of the particular material start changing, and that if the structure of that particular material start changing, the property is also changing because they are in the coexistence between the structure and the property in between them. So these are the orthorhombic type, another kind of a crystal structures. That is the simple, that is the A is not equal to B is not equal to C, but the angle that the alpha, beta, gamma is equal to 90 degree. As you can see, these are also categorized in that particular body centered, base centered and face centered. That is the base centered is the another thing which are different from the cubic center, that is in the base from the upper and the lower part. And then the moving to that monoclinic, you can say there is a shift between that particular angle of that things. So that is A is not equal to B is not equal to C, but in that particular coordinate you can see there is a tilting motion of that thing. So that tilting is also providing some kind of a structure to that particular materials. So what is that means? That is how that particular properties are also defined. So that is the alpha is equal to gamma, but B is not equal to that particular things. So that is how that is differentiate from another. So and another kind of crystal structure, that is rhombohedral and the hexagonal and triclinic. So these all are the various basic crystal system arrangements of that particular atomic arrangement. You can say the atoms are arranged in this particular crystal system in the space lattice to arrange themselves in that particular systematic manner and provide a various kind of a property to that particular component, or you can say the particular material. So in the rhombohedral, A is equal to B is equal to C, and but the angle is different. Alpha is equal to beta, but is equal to gamma, and gamma is not equal to that. These things are not equal to the 90 degree, as you can see there, that is in the front of that. And the hexagonal, that is the A is equal to B, but C is not equal. And in the similar thing, that is alpha beta gamma is 90 degree, but alpha beta is the 90 degree, gamma is the 120 degree. That is how the hexagonal is created. And this triclinic is showing the totally different. You can say we just shift that particular thing from one angle to another angle. A is not equal to B is not equal to C. Alpha, beta, gamma is not equal to 90 degrees as well. So these structure, this crystal system is defining by some kind of a structure, and that structure we always discussing the structure related to the property. The criticality and in the property, the arrangement in the particular things will define the various properties of the particular materials. So that is how we will only focus on the cubic system, because all these shapes are totally intricate, and that is the study of that things will be in the higher level of study, that particular metallurgy, how that particular things are happening. So we will only focus on that particular cubic system. So these are the systems with the example of that particular materials which are showing that the arrangements and how this triclinic K2S2O8 and K2Cr2O7, and the monoclinic is showing AS4S4 KNO2 CaSO4 2S2O, and rhombohedral is showing the beta SHG and SPASPICACO3. So that these are all the particular examples are related to that crystal system. Now we are moving to that how that particular, as we discussed that we will only focus on that particular cubic system. So now then we are proceeding that how that particular atoms are located in that particular coordinates, in that particular arrangement, in that particular unit cell. So position of any point in a unit cell, the point is defined in that particular atoms arrangements. So that the unit cell is given by its coordinate or a distance from the x, y and z axis in term of lattice vector A, B and C. So you can see from the figure that the distance, the parameter defined by the A, B and C along the axis x, y and z, that the meaning of that things is showing. So the coordinate distance that is defining, and that thus the point located at A by 2 along x axis, B is by 3, means that A by 2 means that is the particular point location. It means that particular atom location is located with this half of that particular parameter at the x axis, that is A by 2. So that is that, as you can see in this particular figure. Sorry, that thing is a little bit, that the A by 2, and in the similar manner that is the B by 3, it means 1/3 of that B position, and that is the C by 2, 1 by half that particular thing. So these sorry, things are defined by all these things. So what is the point coordinate? That's showing the position of any point in the unit cell. That is how we defining that thing. So we will discuss how we are examining all these things that to calculate. So that is calculated by that particular Miller indices, a term which is defining the arrangement of that particular. So that plane in a crystal are described, that particular plane, that is A by 2, B by 3, A by C by 2. So how they are identified and how we calculate that things. So that is the method, the Miller indices. The plane in a crystal are described by the notation. That notation is called the Miller indices. The Miller indices of a plane indicated by the HKL are given by the reciprocal of the intercept of the plane of the 3 axis. So when we got that particular intercept, that is the totally reciprocal of that thing. So how these things are happening in the next point we will discuss. So the plane which intersect x-axis at one lattice parameter and is parallel to the y and z axis, has the Miller indices of 1 by 1 is equal to 1, k is equal to 1 by infinity, that is related to the 0, and 1 is infinity, that is to the 0, and that is how we define that HKL is 1 0 0, and that the Miller indices is 1 along the particular thing. So only one lattice parameter along the x-axis is defining by the 1, and another axis is, that is the, because all the point coordinates is defined by this, so that is how this Miller indices is working. So in the Miller indices of some other planes in the cubic system are is shown in the figure in the next slide, as you can see here. To find the Miller indices of a plane, follow these steps. So these are the particular things we need to follow. So as you can see, the parameter and the axis are provided and the particular indices are provided by the first figure, that is 1 0 0. So how we will define it means that plane is lying only the one axis along the one axis x-axis. So 1 by 1 by infinity HKL, and 1 is infinity. So that is how that particular things are arranged. And in the similar manner, that is the 1 1 0, it means that particular plane is lying in between the x-axis and the y-axis, but the z-axis is the 0. So that is how we define that things. So as you can see, that 1 1 is the total arrangement, the x y z, as you can see HKL. Here is also the HKL. Here is also HKL. So what we need to find out? We need to find out that particular coordinate of that things. So how we will discuss the x along the h, that is the x is 1, y is 0 and z is 0. But that is in the infinity manner. So we are taking that particular, if we put that 0 here, what will happen? It will lead to the infinity. So we will discuss that things in later on, how these things will change, how these things are working. So they determine the Miller indices, that determine the intercept of the particular plane. So along the crystal axis, take the reciprocal, that the reciprocal which I told you, if we take that particular 0, what will happen? Or if we take that particular 0 by 1, what will happen? We will go to that particular thing, not that thing. That was the wrong thing. That what will happen if we take that particular 0, what will be going to the infinity? So that means the infinity plane. So how you will define that infinity plane? It is not possible for that. So we will going to discuss how these things are working. So take the reciprocal, create the fraction, reduce the lowest term and enclose in the bracket. So these are the possible manners in which these things are happening. So for the example, A, B, C, 3 by 4, 1 by 2, 1 by 4 means, take the reciprocal means, that is the 4 by 3 and that is half, that is the 2 and that is the 4. So as we discuss that things, if we take the only the 0, that is the things, if we take the 0, when we reciprocate thing, what will happen? It will lead to the infinity. So we will not go through the infinity, and that is how these things need to be taken care of that. And after taking the reciprocal, clear all the fractions. So how do you will fraction all these things? That means 4 by 3. So it is not possible for that. So what we did is that we multiply all these things by the 2. And these things. So for intercepting all these things, we need to manage that particular fraction, and how we will manage that particular fraction to this, that we multiply by this particular by 6 and this by the 4, and that is how, that is the 6 into 4, that is lead to the 24, and divided by 12, that is the 2. That is the clear the fraction, and that is similar manner, that 6 into 2 is equal to 12 and divided by 4, that is lead to the 3, and see the same 6 into 4 is 24 divided by 4, that is leading to the 6. So that is how we need to minimize that particular things and the clear that particular fraction, and then conclude in the bracket. So what are the next challenges if the plane in the negative section? So how we will define that? If the intercept is going to, like example 1 1 minus 1 by 2 is 1. So in the similar manner we will do that thing which we did in the previous slide. But how we will define that particular negative things, that the negative sign, that particular negative sign will reach here, that is by the bar. It means that particular angle interception is in the negative portion. Means if we are talking about that particular x, y and z plane, so that the particular x, that is a z, that is a y. So if we are talking about the negative one, so that x is related to that negative here, that particular y is negative here, and that z is negative here. So that is how we identify that particular plane in that particular manner. So the plane having similar indices are equivalent face of the cube 1 0 0 0 1 0 and 0 0 1. This is the term as the family of the plane, and these are denoted as 1 0 0, which include all the 1 0 0 combination including negative indices also. Some other equivalent planes are also shown in the next slide. These are the arrangements, and that particular things are showing here. The particular family members that we discuss that things. So that family members, that is the 1 0 0 is the family, 1 1 0 is the family, as you can see. That particular 1 0 0, that arrangement 1 1 0, that is in the different, and that is the 1 1 1. So that 1 1 1 is also including some kind of negative things, that is the negative, that is the negative, and that is how we define all these things. So these are the particular so that is also showing in that particular figure. Note the shift of the origin from the blue to red circle for the negative indices, because that blue is showing for that particular positive one, and that particular means that the particular thing is shifted here, that is a -1. That particular x-axis is shift to that particular plane. So plane in the hexagonal system is the very intricate, as we discussed that these things are little bit intricate, but we will discuss. In the cubic system, all faces of the cube are equivalent, that is they have similar indices. However, this is not the case in the hexagonal system. The 6 prism faces, for example, have the indices 1 0 0 0 1 0, minus 1 1 0, minus 1 0 0, minus 0 1 0, and 1 1 0, which are not same. So these arrangements are a little bit typical to understand, and that is how these things are to be calculated. So this is the indices of the 6 faces. Now become this from the family plane. Now as we discussed the point coordinate or the crystal directions, how these directions are showing and how these things are happening. So before proceeding all these things, we need to conclude all these particular structures, arrangements that we point from the point coordinate. We define the arrangement of that particular indices or the arrangement of that particular points. Now we will discuss how in which direction these all are moving, and that is how it works. So the direction in a crystal are given by specifying the coordinate u, v, w of a point on a vector, that is r, u, v, w passing through the origin. So r, u, v, w, u, a plus v, b plus w, c. It is indicated as u, v, w. For example of a direction, the 1 1 0 lies on a vector r 1 1 0 whose projection length on x and y axis are 1 unit in terms of unit vector a, b. So direction of the form of family like 1 1 0, 1 0 is 1 and 0 0 0 1 1. So these are in the same family, right, as that particular thing we discussed earlier. So how we will define that particular thing? That is how this particular thing is defined by that 1 0 0, that is the family of 1 1 0, and this is the family showing 1 1 1 1 1 1. In the similar, we will conclude that particular things is here also. That particular family arrangement is showing here 1 0 0 0 0 1, and that is your z-axis. That z-axis is not shown here. Yes, that is the z-axis, that particular points. So that is how the family of the plane is defined, the 1 1 0 and 0 1 0 and that is the 0 0 1 and 1 1 1. So these are the family of the plane, that is how they are in the showing in the particular directions, and that the direction is defined by the positive and the negative. As we discussed, if we are indicating in the negative direction, that is denoted by the bar. So that is how the crystal direction is to be identified, and that identification, as we discussed, how that is to be calculated by that particular things from the figure. So the crystal direction, how to determine the crystal direction of a line in a crystal, that we need to find out the coordinate of the two end of the line and subtract the coordinate, and or draw a line from the origin parallel to the line and find the projection length of the x, y and z in term of a unit vector a, b, c, and then convert the fraction, if any, into the integer and reduce to the lowest term and enclose into the UVW, and that is how it happened there for the particular hexagon. So like all the plane, we focusing on these things. So these are the crystal direction of that particular hexagonal. So like plane direction in the hexagonal system are also written as UVT, that the particular point included W. If UVW are indices in the 3 axis, then it can be converted to the 4 axis, that is the UVTW, and that is how the using of that particular relation is happening. U minus T, V minus T, W is equal to W, 2U minus V by 3, 2V minus U by 3, T is equal to minus U plus V is equal to minus U plus V by 3, and W is equal to W, and that is how this family of the plane and their direction is shown by this particular. So from this we are concluding our lecture, and we will discuss the more regarding these structures and the planes of that particular crystal structures in the next class. Thank you.